So the spiral life cycle model for the development of the software has objectives here. This one has something that's different is they also consider the risk assessment, right? So you look at the risk and how you're going to manage risk. They have risk management. Okay. So the risk could be if the objective, if I said, I'm asking you to make an Android interface, an iOS interface for a third assignment. That's going to be risk assessment, right? Someone may take longer time to do that. And it's going to involve with a timeline that you're not going to get it done within 4 weeks till date. Then we have to go back and readjust the requirements. So that is spiral like that. You access and you, okay, so look at the development, said, no, I cannot do it. It's going to take longer, right? And validate it and readjust your objective again and again, right? That's spiral. Alright, so this is just an object-oriented programming review. We already know that, which is we work on the user, right? User attributes. That's just the date. Showing you how to organize your classes into packages, inheritance. You extend, right, to use is a relationship like that, right? Extends. So we talked about that already. This is UML diagram. Extends, right? Symbols, object. You know, all Java classes extends from objects. Increment date extends from date, right? And this is the symbol for usage, right? So this use the increment date. This class name a date and my date use date. And we know when we create packages, right? And package pretty much just put the word package on the top of your class. That's how you create package. Like we try to package them into like controller, model, right? View, things like that. We can separate them into that. And we have like all the collections as a package of all the data structure utilities, right? So now that's just review of Java. Now that structure, we talk about that, right? You can re-implement the data structure, either use array or linked list. And at this point, we understand what's the difference, how we do it. But they are related to the big O efficiencies. So that's why we're going to talk about that. And we know this is stack architecture. This is queue, right? Stack is first in, last out, or last in, first out, right? Queue first in, first out. And list, sorted list is in order. So this is what we have done so far in assignment 2, right? So in assignment 3 and 4, 3 we're going to look at binary tree here. We're going to have a tree structure. And 4 you're going to use graph. Graph just like when you use GPS, it's going to find a faster route, right, to each node between cities. That is structure. So we're going to talk about that in assignment 3 and 4. Now, this is just review of Java, like by references, right? Object and this array. Like if you have in A, in B, when you say in A equal in B, you pretty much just replace the values of int A, right, with in B, which is 10. But if you look at object C1 pointing to circle, big one, C2 small circle, when it says C1 equal to C2, you actually move the pointer to that instead, not the values. So that's why when you're dealing with these references, you have to be careful, right, to use if you do that. That's why we have to do dot equals instead, right, or dot compare to. And the object that you see like that is going to be garbage collections. Just like when we move your pointer when you use linked list, You don't have to worry about that because we have garbage collections cleaning it out. We call deallocate of the memories. It's dynamically memory management. It happened in Java because Java has GRE. But in C, C++, you have to do it on your own. You have to clean it up. Otherwise, your program will be hanged or run out of the memories. So now looking at big O analysis, right? This is how you're going to measure efficiency of your algorithms. Okay. Like we said, there are many ways to solve the problem. There can be more than one algorithm to solve the problem. Like if you look at this map, you are here, and if you want to go to, if you're hungry, where would you go? Joe's dinner, right? So there are many ways to go to Joe's dinner, Joe's diner, right? So you can take the big highway and then it's on your left. Or you can just make a left turn on the winning country road and make a right turn, and your Joe's diner is on your right, right? That's an example. Which one is more efficient? Big highway. You can tell, right? This one is going to be less efficient. Our goal here, we want to be able to measure your code that using big O. Okay. So when you learn this further, they have like a small O too. And they have something in between. Omega. And they have beta. Big omega. Okay. And you learn that. It's just look at the lower bound. This one look at the upper bound. Okay. Small look at the lower bound. So at this point, just focus on just big O to measure the worst case. That is the upper bound. Alright. To measure the complexity of an algorithm, we attempt to count the number of basic operations required to complete the algorithms. To make our count generally usable, we express it as function of the size of the problem. So let's look at counting operations here, right? Return true if sum of numbers in array is greater than 0. False otherwise. So we said if n equal to size of array, the number of operations required is n plus 3. So you're going to look at this, set sum to 0, while more integers, set sum to sum plus next in. So if sum greater than 0, return true, else return false. Let's explain. Like whenever you see n, is loops always n. And we said when you set sum to 0, this is 1. When you evaluate sum greater than 0, that is another 1. Okay. And I think the cost that return, it will cost you another 1. So that's n plus 3. So now, if you look inside the loop, it could cost you even more if you have more expressions. If you look at that detail, it's going to be too complicated. Okay. So rather than count all operations, like a fundamental operations and operation that is performed the most, and count it instead. For example, if the problem is to sort elements of an array, count the number of times one element is compared to another element. Only count comparison operations when comparing sorting algorithms. So we measure the complexity of an algorithm as the number of times a fundamental operation is performed. Right? Fundamental. We don't care about too many things in small. Only look at fundamental. So represent as a function of the size of the problem. For example, an algorithm Algorithms performed on an n elements array may require 2n squared plus 4n plus 3 comparisons. And we know that how we add that up, just like what we get here, right? Like we said, if we have something in the loop, like another add, it could be 2n, right? It could be 3n, right? If we have nested loop, it could be n squared. So that's how you start to construct the equation like that, right? Plus 3 could be that set to 0, right? Comparison and so on, right? And you happen to, like in this program, you can tell that there are two loops, nested loop here, and they have maybe some adding of statements, 2 of them in there, right? That's why you have 2n squared. And they have another loop. We have another 4 statements in there, right? That's why 4n plus 3 other, right, statements. Make sense? So you translate your code into the expressions. And then we want to look at big O, notation express computing time of this program. Okay, in the function that increases most rapidly, so which one should be rapidly? N squared. So it's n squared. So this big O is n squared. We don't worry about, because if you think about n is 1 million, this 3 means nothing. So we can omitting it. Right? 1 million squared is a lot than just 4 million. So we just look at this efficiency big O of n squared. So that's how you look at big O. Now you may start to see the common orders of the big O or the magnitude here. We have big O of 1. It's called bounded time. The amount of work is not dependent on the size of the problem. We have log n is called the logarithmic time. Algorithms that successively cut the amount of data to be processed in half, like binary search. You look at half when you look at the name on the phone book. N is called linear time. Adding together the elements of an array is big O of n. You have to add everything in an array, then you have to look through array list. N, that's n time, right? N log n is called the n log n time. This is about, you have to do sorting first, like quick sort, n log n, heap sort, merge sort, and we're going to look at this in chapter 10 in details. N square. This is called quadratic time. Like normally sorting algorithms is going to cost you n square. Like last time we looked at the selection sort. Selection sort, you have to loop to find the smallest number and put it first. And then you have to loop the rest of the list and put it first over and over again. So you need at least 2 loops. So n squared. 2n is called exponential time. So these algorithms are extremely costly. Now let's look at the growth rates. If n is 1, log n is about 0. 256 log n is about 8. If you can write your program with log n, which is binary search, then it's only 8 to get to find the result for 256 records. But if it happens to be linear, which is n, 256, right? If it's happen to be n log n time, then it's 2048. If you happen to have n square, 65,000. N cube, 16,000. This is like 3 loops, right? 3 nested loops. 2 to n. It's just infinite, right? A lot. So there are cases for complexity. best case, average case, and worst